So welcome back. We're going to solve some one-step inequalities. Again, inequalities are going to work a whole lot like equations, except of course, inequalities, the symbols are a little different. We have is less than, is greater than, is less than or equal to, is greater than equal to. Those are our four inequality symbols that we use quite a bit. So let's look at our first inequality. We have some number plus 1 has to be greater than or equal to 4. So in this, what we pick up on is we got a greater than or equal to symbol. So in our problem, we don't necessarily have a balanced scale. It's kind of tilted. Actually, I don't think I tilted that right either. If this is greater than, that's probably going to make it tilt more like this as well. So this is not going to be balanced per se. It's going to have more of a slant to it somehow. So if we're saying this is greater than 4, if the 4 is over here, the other side has to be greater than or equal to 4. So what this is saying is, if I can make this a 4, this statement is true because 4 is equal to 4. But that's not the only number. What numbers are greater than or equal to 4? Well, 4 is equal to 4, but the numbers that are greater than 4 cannot even be counted. So what happens to these inequalities is we don't actually get a single number as our answer. Our answer has a lot of numbers that can satisfy the condition. So when we solve this, what happens is we're going to graph our solution on a number line to represent our solution because it has too many solutions to name them, so we use a graph to represent the solution. So what I can do to solve the inequality is, again, just get the variable by itself. I can zero out the 1 using a negative 1. And I get r is greater than or equal to a 3. So r is greater than or equal to a 3. That means r has to be at least 3 to make this work. If you pick a 3, 3 plus 1 is greater than or equal to 4, but it can also be greater than 3. So if I pick like a 4 or a 5, notice that this is going to make it a true. And don't forget, we're not just talking whole numbers and stuff, we're also talking about those decimals and fractional answers too. So to describe the solution, the first thing I pick up on is greater than or equal to. That's this symbol over here, greater than or equal to. We call this a closed-ended concept. Closed-ended means I have to include the endpoint. So I use what we call a solid dot. So what I do is, on my number line, I graph the number 3, 1, 2, 0, 1, 2, 3, so 3 would be there. And what I do is I make a solid dot at that spot. And my values have to be greater than or equal to 3. So what that's telling me is I need to shade to the right of 3. So my solution becomes then a shaded number line, if you will. So everything to the right of 3 is going to satisfy this condition. Notice how I shaded that arrow, because that arrow, when I shade that arrow in, that means my solutions just keep on going forever. And another word for that in math is we refer to that as infinity. So notice how, to keep it true, it's actually got to be out of balance, if you will. This has got to be heavier. Okay? And also, when we pick up on this greater than or equal to symbol, since 3 is included in the solution, we use what we call a solid dot there. So let's see if I can bring that to light a little bit more. Let's solve this inequality. Again, to get the variable by itself, we see division. When we see division, we know we can use multiplication to solve it. So I can multiply this side by 3 as long as I multiply this side by 3. Notice how these 3's will actually divide out. You get n is greater than 9. So on this one, we have a greater than symbol. So any number greater than 9 should work. Notice that if you use 9, 9 divided by 3 is 3, but 3 is not greater than 3, so it's not part of the solution. So when I graph my solution, I identify the 9, but when I identify it, we call this open-ended. We use what we call an open circle. So I don't color that in, I leave it open. If it's equal to, we make it solid, but open for the greater than symbol. We do not include that endpoint. And again, it says greater than, so that means we have to shade off to the right here. So everything to the right is going to satisfy it. And also shade in that number line there. So your graph is going to look something like that. So you're going to actually shade in everything to the right of 9. And what that means is everything that's to the right of 9 is going to satisfy this condition. And you can try it. Picking a number greater than 9, put it in, and you'll discover that it is greater than 3. Let's look at this next example. I'll put a little asterisk there. Pay attention. So again, I want to get x by itself, so notice how I got that -9 there, and I want to divide each side by -9 to get x by itself. And that should flag us because in our earlier video we noted that if I want to keep this statement true, if each side is multiplied or divided by a negative, I have to flip that inequality symbol. So when I do that, I have to come down with this symbol being flipped, less than or equal to 8. So what this is telling me to do is pick the solutions that are less than or equal to 8. So on this problem, again, 8 is part of the solution. Notice how it's less than or equal to. But notice that since it's less than or equal to, this is what we call closed-ended. So closed-ended, we need to use that solid dot there. So that's why I colored that in as a solid. Less than 8 means you need to go left of 8. So I need to shade everything the other direction. So anything to the left of 8 should satisfy this. So if you pick any number less than 8 and put it in for x, it should make that statement true. For instance, let's pick the number 2 there. -9 times 2. Well, it's -18 greater than or equal to a -72. So remember on a number line, here's 0, -18 would be here, -72 would be further down the road. And we learned that the number to the right is actually worth more. So -18 has more value than a -72. So it does hold true that -18 is indeed greater than a -72. So that does check out when I verify it. So any number less than or equal to 8 will work for this problem. So when you see inequalities, you will start to see the solution being represented using a number line. So it's represented 2 ways. Right now we're using this inequality statement to describe our solution, and we're also using a number line to describe our solution. Inequality, number line. Inequality, number line. So we represent that solution 2 ways. So stay tuned.